ברוכים הבאים לקורס מכניקה קוונטית 1. הקורס אמור להינתן באנגלית, רק אני לא רואה כאן מישהו שדורש את האנגלית, ואני מניח שלכם יותר קל כרגע עברית, או שאתם מעדיפים אנגלית. יידיש. מה שאתם רוצים. בואו נתחיל קצת עניינים מנהלתיים. זה קורס שרשומים עליו מעט תלמידים, סדר גודל של 10. עכשיו, אני לא רוצה לעמוד פה ולדבר לצורך הקלטה. זאת אומרת, אם אתם רוצים ללמוד מכניקה קוונטית מההקלטות, הכל טוב, אבל אי אפשר לנהל ככה שיעור. ואתם יכולים למצוא הקלטות יותר טובות, מסודרות בצורה יותר מתאימה למבנה של קורסים מתוקשבים. אתם יכולים לקרוא, הכל טוב, אבל בשביל שיש שיעור המשמעות שלו זה שננהל דו-שיח. ואם אני מדבר רק על עצמי, זה קצת סותר את הרעיון של דו-שיח. אז אני מבקש שתנכחו בשיעורים. עכשיו, אני שונא להיות גננת, אבל אם אני אראה בשיעור הבא שהנוכחות תישאר דלילה בצורה הזאת, אני אצטרך לעבור לשיטות של גננת, לקרוא שמות לפי החוקים של האוניברסיטה. מי שנהדר יותר משתי שיעורים אפשר להוציא אותו מהקורס. אז אני לא רוצה להגיע לזה, אבל בכל זאת אני גם לא רוצה לדבר עם עצמי. Okay, now we'll switch to English.
Excuse me, is this class in quantum mechanics?
Yes, this is a course in quantum mechanics.
Sorry, I'm late.
And, well, till now we spoke in Hebrew because there was no demand for English, but since you're here, we'll switch to English. Okay, so what I said is that basically it's a small course, something like 10, 11 people are at the moment registered to the course, and therefore I request that you come to the courses because we want to have it interactive, to have some discussion, to ask questions, to hear what your friends are asking, and somehow learn. Okay, so let's start with some administrative tasks. Okay, as far as I remember, the grading of this course is composed from two components. One of the components is simply the final exam. If I remember correctly, it's 70% of the final grade, and the other component is performing the homework. Now, we all know that to perform the homework, all you have to do is ask chat to perform your homework. We're aware that that's what you're doing, but I recommend that I don't care that you interact with chat. Actually, it's sometimes a very good way to learn things. But understand what you're doing there. And the reasons that you have every week or 2 weeks homework assignment is that if you come at the last moment, a week before the exam, cram, binge 30 or 40 hours of lectures in double speed and appear for the exam, unfortunately you'll fail. Because especially in the course in quantum mechanics, you have a lot of new material, conceptually different from what you are used to, and it takes time. Unfortunately, human psyche needs time to get used and understand new ideas and new concepts. Quantum mechanics is full of new ideas and new concepts. So I request that do the homework at time, submit it. As I said, you can seek the assistance of chat, but try to understand what you're doing, because in the last moment you won't be able to understand everything. Okay, so that's 30% of the final grade. Now the lecture, we have 3 lectures scheduled between 2 and 5. What I'll usually do is give an hour and 15 minutes, depending on how the lecture goes, have a 15-minute break, return, and we'll end something around 4:30 to give you a bit of a breather before your next class. Okay, books. Quantum mechanics has tons of good textbooks. You have to find whatever is suitable for you. Anything that has introduction to quantum mechanics or quantum mechanics is usually quite a good book. I see here Sakurai. There's many good textbooks. I'm not sticking to one. So, and more or less all of them cover the same material, more or less in the same way, so it doesn't make a huge difference which one of them you choose. Okay, questions? No questions. Good. So we are switching to the given part of the course. So, actually, what did you do until now in physics? Most of you have 2 years of physics courses. You're allowed to answer. I'm not
Okay.
So you're second year, so you have a year.
Yeah.
All of you? Well, you're...
No, I'm in third year.
I actually returned after 2 years.
Okay, so all of you did mechanics, electricity, statistics, waves, all these courses. Okay, what did you actually learn to do? Please state your name so I start to know who you are. When you're speaking, one by one, I'm not functioning well in parallel.
Sorry.
So what's your name?
Yeah.
Okay.
So we solve the problems with like specific
Okay, so actually you summed up quite correctly what you have been doing here in the last year or a couple of years. You solve problems, okay? But what specifically did you want to know about the problem? Let's take mechanics, the simplest case. Okay, you have a particle. Let's put it to start to ask any question about this particle, what did you need to know? Can you tell me your name?
I come from China. The building.
Okay, so what's the name? I can.
詹香春 VHANAN.
Jean. H.
C instead of D.
Oh, that's a Z. C.
VHEN.
Zhang Yang Shen.
Yes.
Close enough, at least.
It's hard to pronounce.
Okay, so shorten Zhang will be good enough. Zhang Shen. Okay, so this. So we have this particle. To solve a problem regarding this particle, what do we need to know?
The mass, the position, and the moment.
Correct. Very good. So we need position. X vector. This is like R, x1, x2, x3, x, y, z. Fortunately or unfortunately, we're living in a three-dimensional universe. And momenta. So what do we call these attributes in mathematics?
Vectors.
No, these are vectors, but okay, physics, what do we call it? Initial conditions. Someone has to come and tell us where is this particle and what's its momentum. If we don't know that, no matter how great mathematicians we are, we won't be able to answer any question. Now, typically, what kind of questions do we ask about this particle?
Where is the particle? What's the velocity?
Exactly, we want to know under some external forces that exist in the system, and I don't define what is a system. Let's assume there are some forces anywhere in this here, and we're asking what is the trajectory that this particle takes, and where will we find it after some time has passed? Right? Now the forces could be anything, could be electric forces, magnetic forces, mechanical forces, whatever, but the question we ask is, where will the particle be after time t? And what will be its momentum? And in principle, we can take t any time that we want. We can check it along the trajectory here, 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 wherever. And our only problem is that the mathematics could be hard, but at the end of the day, we could solve any problem as long as we got the initial conditions and what are the forces here. Couldn't do it analytically, we can do it computer simulation. Okay, that's classical physics. Now, there's a caveat, a point that is not completely true about what I said here, and that has to do with chaos systems for which the initial conditions will change the result exponentially as dependent on time. We could have a problem because in reality we never specify x and p to arbitrary correctness, to arbitrary precision. Always there are some mistakes, and if two initial conditions that are very close at large time deviate exponentially, even in classical physics we will not be able to predict the behavior after a long time. Someone can give me an example of such a system? Something that all of you recognize from your daily life. Weather. You can measure the pressure and temperature and direction of wind and whatnot to very good precision, feed it to a computer, get a forecast for the future. What will be the weather in the future? Fortunately, it works for a few days, perhaps a week. No one knows to calculate for longer, and not because we can't write down the forces. We have exact description of the equations that are relevant. Just if we miss by a bit the initial conditions, after a week, 10 days or something like that, we'll get a completely different prediction. Therefore, we lost accuracy. Therefore, we can't say anything about that. That's a classical system. Okay. So, quantum physics. All of you heard a course on modern physics, right? Okay, so what do we do in quantum mechanics? What did you do in modern physics? Just
solve for
just your name, please. So I said. Okay.
I guess the goal is the same than in classical mechanics. It's to predict the state of a particle at some time.
Okay, so we could say, well, we want to do the same, which will be correct in quantum mechanics. We want to know the initial condition. We want to know the trajectory. We want to know its position and momentum at every time in the future.
But it's impossible because of
it's impossible. Let's put a point here. Why that would be the goal of our course. Now, I'll try to give you a flavor of what we are going to do in the following semester. Not all of it will be understood at this point, but I hope it will. We can use it as a roadmap towards what we are trying to do in this course. Okay, so quantum physics or quantum mechanics changes completely the language of what we are doing. What can we ask? What is initial conditions? What can we say on what happens in between? All of this is different in quantum mechanics. And unlike, let's say, relativity, where Einstein sat for a couple of years, thought how to combine a constant speed of light with Newtonian mechanics and came up with a solution. Into quantum mechanics, physics was dragged screaming and kicking all the way for a quarter of a century. Around in the 1900s, we had black body radiation and Planck's solution. The final description of quantum mechanics came actually in 1927, when Dirac gave the final mathematical structure of quantum mechanics. In between, we had a lot of attempts to understand what happens, Bohr's model, Sommerfeld's model, de Broglie, everything, even a description of a wave function and an equation for a wave function, the matrix mechanics of Heisenberg in 1925, Schrödinger's wave equation in 1926. But, truth be said, until today there's still an argument what is described by quantum mechanics. So it's a very interesting situation where basically we know to calculate a lot of physical quantities. We know to give answers about how a system will behave, and astoundingly exact. We can calculate the energy levels of the hydrogen atom till 10 or 11 digits beyond the decimal point. So it's the best theories that we have. On the other hand, what does it mean? What does it describe? What is the real nature of this theory? There's arguments, and I would say no one really understands. So what does it mean? So we don't understand this in the theory? No, we understand exactly how to work with the theory. The problem is that it's very abstract, and the deeper meaning of it doesn't sit well with our intuition. And some of you have probably heard this expression in the popular literature, shut up and calculate. Okay, when you come to study quantum mechanics, understand the mechanism. Actually, around the third or fourth lecture in this course, you will have an exact algorithm how to solve any problem. Let's be a bit more exact, any one particle problem that will be given to you, and it's an algorithm. And if you implement it correctly, you end up with a correct result that can be got. You can go to the lab, measure, and you'll verify it till whatever precision you feel like. On the other hand, what exactly stands behind it? In physical concepts is much harder to answer. There are different schools of understanding. Some of you have heard about the Copenhagen interpretations. Others have heard about, perhaps say, heard about many world interpretation and anything in between, Bohm's interpretation. There's a lot of interpretations. The big problem is that all of them, when you try to predict a result of an experiment, gives the same prediction. So how do you distinguish between them? Usually you distinguish between physical theories. If they give you different answers, you go into the lab, measure one or two, and decide which is the correct interpretation. Here, until now, we don't have any such definitive experiments that can really differentiate between all these interpretations. So I'll mention them, but it's important to understand that at the moment it's more an algorithm how to calculate than a deep understanding of what's the physics of the world. Yeah.
Which one we gonna use in source?
Doesn't matter.
Oh.
The nice thing is it doesn't matter. And I'll explain in a moment why. Okay, so we had for a single particle in classical mechanics, we need 6 numbers, 3 for x, 3 for p, and how they develop with time basically is what are the questions that we're interested in. What do we have for quantum mechanics? For quantum mechanics, we have this strange object psi, which is a wave function. What are its parameters? So, you have seen perhaps some solution.
The expression of meditation and how it's how develops in space
And time.
yeah.
Okay, so it's some function. Perhaps you even solve Schrödinger equation for some particular potential or something, which depends on position and time. And basically, the initial condition, equivalent to this guy, would be at some time, let's call it 0. already here something disturbs me. What does it what looks problematic here? What's your name? Yeah?
Maria.
Maria.
I have no idea.
Counting. Parameters.
Oh, we used to have 6 there, and now we have less.
We have 3. Time we had also here. And what's special? Previously, both x and p were important. Now only x is important. Okay, so first of all, this statement is not true. What do I mean? We could move to an alternate representation, and we'll learn how to do it, and have our wave function depending on p and t. Not necessarily on x. So at least part of the problem is answered. As initial problems in quantum mechanics textbooks and lecturers like to give you something psi of x, but there's no reason at all not to give you psi of p. It's completely equivalent. You work with whatever is convenient. Okay, the deep reason why we have x, we don't have x and p together, and it was mentioned here. Someone can give me the answer why we have either x or p.
Maybe it's because we have the delta x times delta p equal has to be bigger than h divided by 4.
Exactly, the uncertainty principle. We can describe it in the language of x, we can describe it in the language of p, we can describe it in the language of both. Okay, so we have here our wave function. Okay, a very bad name. Why is it a bad name? Because what do you think about when you hear a wave? Yeah, some water waves, electromagnetic wave, something that changes in time, in real space, right? This wave function doesn't exist in real space, although you have here an x. It's not a classical wave in real space. That's why de Broglie and Schrödinger's initial understanding was wrong. It's when you get the wave function of an electron around the hydrogen atom, it's not that it's some modulation that exists everywhere around this the hydrogen atom. No. So where does this entity live? Okay, before that, what is this entity? Now, life, for historical reasons, people usually start with a wave function to describe a physical system. Why? Because it's one particle Instead, I want to describe a much simpler wave function. It's not a function, it's a vector. And what is a vector?
Vector is something that has the amount and the direction.
Okay, let's go back to computer science, those of you who study it, or mathematics, those of you. No, a vector is just a list of numbers, right? 1, 2, to the end. A function is this entity when you are taking an infinite number of entries in the vector and non-countable, because x is real. Okay, so what do we know about this entity? So leave the interpretation of direction, because we know in computer science we can have vectors that describe stuff that is not direction. But this can define a space, a mathematical space. And this guy and this guy and this guy, all of them live in a space that is known as Hilbert space, and we'll define it and understand what it means. In very simple terms, a space is something where you can combine entities in it, you can multiply it by a scalar, you can transform it into other entities in this space. Even those of you who never in their life heard a course in mathematics can understand this concept. Let's say the real numbers are a field. Why? Because you can combine two real numbers and get a new number, which is still a real number. You can multiply it by a scalar, which is another number, and it's still a number. The natural numbers, you can subtract one from another and get. Natural numbers are not a field. Why? Because natural numbers greater than 0, 0, 1, 2. Take 1, subtract 3, you have a number that's not 0. Not in the field, so that's not a field. Okay, so basically what we are doing in quantum mechanics is taking a wave function at times t0, using the Schrödinger equation to answer the question, how will it look at time t? So basically, let's choose one representation. Okay, so this is the equivalent of taking a particle at point x and p and asking what will be x and p at time t. In quantum mechanics, we take a wave function at some time, t equals 0, and ask what will be the corresponding wave function at time t. Yes, please.
Okay. When doing the last scalar thing, where that we have false.
I didn't say. I didn't say any. What's the force? These are things that will determine how the Schrödinger equation looks like.
Oh, okay.
I didn't say anything how this Schrödinger equation looks like. I didn't even give you a recipe how to write it down. That's why we are.
So it's how
So if I would like to be a mathematician, I would say it's some operators that transforms this vector into this vector, which is time dependent. Now it's very abstract. I didn't say anything. We will spend a lot of time on writing down the appropriate Schrödinger equation for different forces or different physical realizations. But what it does at the end of the day, the same as I didn't describe what is the force here and what will be the trajectory here. So what I do in quantum mechanics, start from a wave function, progressed in time according to some rule, which I call it Schrödinger equation. If I would have described it as a vector, I would call it a matrix, which is a matrix mechanics. So the difference between Schrödinger and Heisenberg was just on, one was working on vectors and one was working on wave functions, but it's the same conceptual framework. Took Toorak to understand that they are both describing the same thing. Because at the time, Schrödinger insisted that that's some wave in real space. But it's not a wave in real space. It's a vector or a function in some abstract field space, which is the Hilbert space. We'll spend some time on the relevant mathematical definitions. Okay, lovely. So I have this entity. Give me it at time t equals 0. I'll tell you how this entity looks at time t. That's extremely amusing, but what we are doing here is physics, not mathematics. What can I do with this wave function, and how do I connect it to reality? Okay, so I'll interject a bit of the interpretation. Many world interpretation is, you're asking the wrong question. This is reality. Hilbert space is a reality. Sorry, you're feeling that real space is reality. You're wrong. Okay, very nice, but we're still living in reality. How do I connect to something I see in reality. And so one pillar of quantum mechanics is a wave function. Second pillar is to connect with reality, which is, someone knows?
Taking the square, if I remember.
Yes, but what is a physical process?
Running an operator.
Excuse me?
An operator on.
Physical operator is a mathematical entity. It has something to do with operators, but measurement. So in order to say something about a physical quantity, I have to perform a measurement. Until I perform my measurement, this is a description and it's well defined mathematically. I don't know how to connect it to something that I see in real space, something that I see in everyday life. Now it's very strange. We are talking about things that are not connected to our everyday intuition. It's well defined. I can do the mathematics. Everything's well. I have a definite prescription how to treat it, but I don't have any intuition what it really means. So I'll give you an example, and that's perhaps the best known description of quantum weirdness, strange things that happen in quantum mechanics. Double slit experiment. I release a particle here which goes in that direction. Okay, so in classical physics, I gave you X, give me also P. I do the calculation, it runs into this screen. It won't go through, it comes through a hole. It will go through, and I'll be able to answer if I sit here and look, put a screen and look where it hits. I would be able, if it has this thing, it will hit here. I will get an answer. If it hits here, if the initial condition is different, I'll have nothing. Okay, end of story. Okay, what does quantum mechanics tell me? Tells me put the wave function at the initial condition, t equals 0, which somehow describes the particle here. We'll talk how to prepare it in an initial condition. Because here, not only the measurement is not clear, how do I prepare a system in an initial condition? It's also not so clear. It's not clear at all. Let's assume that I can. Give you a short caveat. No, you can't do it, but let's leave it. And then you sit here on the screen and you perform a measurement. And you see that it hits here. Not somewhere in between, somewhere where you didn't expect it to appear. So, what does quantum mechanics tell me? tells you take psi x till t equals 0 as the initial condition. Work with the Schrödinger equation, you'll get at time t some other wave function. Okay? Square your wave function. Y square, we will discuss. Why I put absolute value? Because the wave function is a complex number. Saying every entry in the vector here is a complex number.
It's intensity.
Hmm?
Is it the intensity of the wave?
In classical terms, it would have been the intensity. Now, we leave the classical interpretation at all, because now suddenly I'm telling you a total different story. If it would have been an intensity of the wave, I would come and say, well, this particle is spread throughout the screen here with some density psi squared. That's a classical wave. Quantum mechanics? No, this is completely wrong. What do you do here? Okay, this guy is a probability. You have some probability of measuring it here, some probability of measuring it here, some probability of measuring it there. What is the probability? Psi squared. So the wave function square tells me the probability of measuring this particle at time t at some location on the screen. If I'll go and repeat this experiment again and again and again and again, starting from the same initial condition, I will get on the screen some pattern that corresponds to pi squared. And then I'll know something about the wave function square. Now for a single measurement, all I can say is probabilities. So, we have this very strange and hybrid construction. What do I mean by hybrid? This part is completely deterministic, right? I put it in my mathematical machinery, crank it, get an answer what happens in t. I know the wave function at t at any degree of accuracy that I want. Then I ask, if I now measure at t, what will I see? I'm only giving you a probability. Well-behaved development in time, then something happens and I'm seeing the particle at one given point. Extremely strange. This is a well-behaved continuous development. Here I have, someone knows how it's called? Wave function collapse. Some of you heard the words collapse of the wave. The measurement is not a continuous development in time, just at the moment I measure, I see the particle at a given point, and from here on, I don't work with my initial state. I have here a new initial condition because I measured it at a point. And from here on, I can go and develop what happens if I want to ask what happens at xt prime. I'll start again with my machinery of quantum mechanics and answer you the next question about the continuous. What do we see from this description? We never ever are able to describe a trajectory here. Why? Because at the moment that I perform a measurement, I collapse the wave function. And once I collapse the wave function, I have a new initial condition for the Schrödinger equation. Therefore, if I measured here and only after here, I don't know to say what was the trajectory because it lived only in this Hilbert space. If I insist on, okay, fraction of a second after I'll measure it, and then I'll measure it, and then I'll measure it in order to get a description, I'm answering a total different question. Because the development in time, if I measure only here, and if I measure at each point, is totally different. Now you run into a new problem. Dozens, hundreds, thousands of books were written about it. No good definition. The initial people who worked on quantum mechanics, like Bohr, said measurement has to do something with consciousness. And Einstein was extremely against it. His famous saying, "I can't believe that a mouse staring at the universe changes the universe," because anything that performs a measurement changed the behavior. Today, this interpretation of consciousness fell out of favor, and most physicists agree as an operational definition is something that leaves traces in the environment. Meaning that if in principle you could have known the trajectory or could have go back and checked this information, it's a measurement. For example, take this. Okay, so for this experiment, if you'll return time after time after time and perform this measurement, you'll get here some interference pattern. Now, let's assume you put a detector here connected to a computer that holds the information in the disk. And then you'll see it only going through here, and you'll get just some peak, one peak, not an interference. Okay, so you know quantum mechanics except for everything that you need to know in order to perform a calculation. But that's the whole philosophy of quantum mechanics. So what do we have? The state of the system is described by a wave function. development in time is how this wave function propagates according to something that is known as the Schrödinger equation. Once you get to a point where you want to perform a measurement, tell me what kind of measurement you want to perform, and I'll tell you the mathematical procedure for how to extract whatever probabilities for whatever you want to measure. Because the same thing as I measured here the position, I could have asked, how do I measure the momentum? Well, I'm allowed to measure whatever I want to measure, right? Till now, you know only how to measure position, and you know to measure position, which is psi x squared, because you were introduced to a wave function described in x. If the wave function would have been described in p, the probability of measuring some momentum would be psi squared. So we need a mathematical mechanism to move from here to here, or to any other physical properties that we want to measure, in order to be able to answer the question, what is the probability of measuring something? So, we have a lot of work. We have to first learn something about Hilbert spaces. At the end of the day, this is just linear algebra. I'll do some refresher about linear algebra, so we'll all be in the same point of understanding the mathematical basis. Then we will have to, still don't know how to write it. Have to write Schrödinger. I have to write a way to extract an interesting physical properties that I want. All this is mathematics. All the physics, you know. Okay, it's a good point to stop, and we'll reconvene in 15 minutes. Oh, excuse me. Questions? Those of you who came in late, about all the administrative things connected to the course, talk with people who were here. Okay, so see you in 15 minutes. כן, אני רואה שיש פה חלק שמסכמים, אני יכול לבקש מהם לעלות או לאתר של הקורס או אליך ישירות. מה היה שם? שם.
אהרון.
אני שמח שאתה...
אז אני אבדוק בקבוצת וואטסאפ. תודה.
שאתה יכול איכשהו להסביר לי בלי להגיד זה משהו, זה קונספט חדש לגמרי, כאילו זה לא איזה משהו של הקשר בין החלקיק לאטומים האחרים שבסלית או משהו כזה? לא? זה משהו כאילו לגמרי שאי אפשר להסביר את זה בפיזיקה רגילה?
הדבר היחיד שאתה...
מאוד מוזר. זה כאילו זה קונספט שאני משער ניסו להסביר אותו, אבל
25 שנה ניסו איכשהו להבין את זה בצורה קלאסית או סמי קלאסית או כמעט קלאסית.
קלאסית הכוונה היא בפיזיקה הקלאסית, נכון? זה מאוד מוזר לחשוב על חלקיקים שיכולים לזוז כאילו שהם אמורים, נגיד אמורים לזוז כווקטור.
חלקיקים שאמורים להיות מאופיינים במרחב הממשי, תחושה רגילה שלך שתמיד אתה יכול להגיד מהו X, מהו P, מה קורה בכל זמן.
כן.
והתשובה היא לא. לא. עכשיו, אפילו ההסבר השלם, איך אתה זז מהדיסקריפשן הזה לדיסקריפשן הקלאסי, זאת אומרת שאתה הולך ודואג בכדורגל, אתה לא דואג לאפקטים קוונטיים. אז אומרים לך זה גדול.
כאילו, בעצם העובדה שזה לא בגדלים קטנים, אומר שפיזיקה זה איכשהו משתנה?
זה היה ההסבר של ברקוביץ, זה הקומפלימנטריות, שאתה עובר ממערכות קטנות למערכות גדולות, אתה עובר מפיזיקה קוונטית לקלאסית. ואמפירית זה פחות או יותר נכון, אבל למה זה נכון?
למה זה נכון? זה כבר נשמע שאלה קשה, וגם אני משער שאם יש לך פיזיקה שעובדת על דברים קטנים, שונה מפיזיקה שעובדת על דברים גדולים, אז חייב להיות איזה משהו שאמור להעביר אותך באמצע, לא? כאילו, יהיה לך דברים בינוניים, משהו כזה.
זה מזוסקופיה.
זה משהו שבקוונטים מכניים משהו, שזה
לא תדעי. זה עד כדי כך מתקדם שאין תשובות טובות.
אין תשובות טובות בינתיים? נשמע אבל מאוד מעניין הקטע הזה שאומרים יש פיזיקה וזה, פיזיקה וזה, זה בינתיים לא פשוט.
זה אחד הבעיות שהיו. Okay, so let's sum up what do we know at the moment about quantum mechanics and actually do a few mathematical properties of wave function before we go into this Hilbert space and linear algebra and what it really means, just to get ourselves all in the same, straighten up our knowledge, which we have from modern physics, and have a concrete starting point. So basically, what have we said? First thing that we said is that So, you want to describe a particle, write down its wave function. And that's all that we know, can know, will know about this particle. This wave function, and this is an interpretation which we will extend in the following lectures, is a probability amplitude. The same way that in a classical wave, an amplitude squared is the wave's intensity. Here, if I want to ask what is the probability of finding the particle at point x at time t, I take the wave function, absolute value squared. It's very important to have absolute value because the wave function can be a complex number. Probability has to be a number. Moreover, it has to be a positive number. We don't have a complex probability. We don't have a negative probability. We can have complex or negative numbers in the wave function. That's completely kosher. It's allowed. But in the probability has no meaning unless it's a positive number, and we'll add smaller than 1. Okay. Is that, so no, I'm missing here something. I have to put a small box around the side. So this is the probability density. Actually, it already tells you something. What are the units of the wave function?
Unitless?
Excuse me?
Unitless?
The
Without?
units. No, it's not unitless. This has units of
Maybe it's 1 divided
1 over
2/3
d. If you are talking about a 3-dimensional universe, it's d equals 3. So psi has units of 1 over L divided by 3, 3 halves.
What is L?
L, length, units of length.
It could be meters,
whatever length you want to use, you are free to choose your units. Here you're not free because probability is a number. So it has to be units of L to the power t divided by 2. Yes, please.
What is d to the third x?
Excuse me for not being a good. Just a small box because it's density, so you have to. If I would have written here a vector, then you didn't need the integrals. Okay. Once we defined it as probability, we know another thing. Particle has to be somewhere. As long as we are dealing with a single particle. Once we are doing something more complicated that we won't do until graduate courses, you know that the photon is not conserved. It can appear, it can disappear. There's no conservation of photons. So there you'll need something else. As for the first 2 courses in quantum mechanics, whatever particles that we described, an electron, a proton, and heaven knows what, it's there, it doesn't disappear. So the probability of finding it is equal to 1. What is Schrödinger equation? And we will understand why it's this particular form and not any other form. For a particle that has forces in its vicinity and they extract force on it, Schrödinger equation is, and first I write the full continuing it here. That is a Schrödinger equation. Give me an initial condition, give me the potentials, which could be time dependent. solve this equation, I'll be able to answer what is psi at any given t, as long as I know it at some t0. Yes?
Is it times, like the thing in the brackets?
Yeah, just I ran out of. So, what do I mean? I go and perform a second derivative according to x, a second derivative into y, a shorter term. I wrote it once in its full glory just because a lot of times you're working only in one dimension and some students don't see immediately how it's expressed for higher dimensions. So this is a shorter version. Oh, and of course the minus is. Good. So I'll show you a simple intuition about how do we get to the Schrödinger equation. It's not a proof, it's just an intuition, but it's to show you that it describes something about what we are, according to the definitions that we gave. What is a wave function, what is the probability, and so on. This is at least consistent with this description. So, I'll give you a couple of minutes to finish. Yeah.
Is V described by X? Didn't we say that we can't describe V by the velocity, by the...
No, this is not. Oh, it's not velocity. This is potential.
Oh, okay. Thank you.
Sorry for not being clear. This is potential. It must be a real number. We'll in a moment use it. It just replaces the F. Somebody can tell me what is the derivative in time of this quantity?
Still 1.
Excuse me? 0. Because
Oh, no,
this
no.
is 1, derivative of a constant is 0.
Oh, no.
Oh,
It
This guy is 1, derivative is 0. It's a cumbersome way of stating that it doesn't disappear. you don't have a reduction in time in the probability of finding the particle anywhere. Okay. I want to rewrite it in terms that you have seen in your courses, hopefully. Let's call this guy rho. So I'm not writing V as a volume, so you won't be confused. But this is just an integral over all the volume. Someone can tell me what is this guy?
God, V is a speed.
Excuse me?
V is a speed.
Yeah, V is a velocity. So let's assume
It's the momentum of the old particle.
no. This is a statistical quantity. Or if you want to think about it, it's a continuity equation. What does it tell you? Let's say I take a part of the system and enclose it by some surface, thus creating some volume delta omega. Now, for this part of the volume, can this integral change in time? Yes, I have only a global constraint. Locally, if I'm looking on some part of the system, it can flow out. But when I'm saying it flows out, what does it mean? It means that if I integrate over the flow everywhere perpendicular to the surface, I'll get the change.
Divergence.
Yeah, it's the divergent Gauss law. It's nothing beyond Gauss law. It's something that at least we're supposed to have ran into at some point. So, So basically, what does it tell you? That the change in the local density is proportional to the derivative of the current, something that you ran into. I would have told you that if it doesn't look familiar, it's good to go and brush up on your previous year's mathematics. The truth is we won't do anything with it beyond justifying the Schrödinger equation. Okay, this is just classical continuum equation. If I have something in a volume and it's conserved, the only way that it can change is by flowing out or into this volume. That's all that it tells us. Okay. What is quantum mechanics? Only this point, right? That the density is psi squared. So, so I just wrote it down explicitly. Okay, and I wrote it down in a cumbersome way instead of absolute value squared psi times complex conjugate. I'm allowed to do it. Okay, so this is the continuation equation, just writing explicitly the derivative of rho. Okay, let's go back to our Schrödinger equation. Excuse me for not writing x and t in every time that I'm writing transition.
It could be the potential, should be add the term before the potential times the phi should be add.
No,
No. Then behind this one should be add
plus this
plus
is
plus.
okay. Potential, not velocity, not anything else. Yes.
What's there? After in that side.
So I'm putting it in the side, and I'll return to it. At the moment, I just wrote the Schrödinger equation. Okay, I want to show that the Schrödinger equation fulfills what's written. Okay, I have a small problem. I have here an equation to psi, for psi, not for psi complex conjugate. No problem, I'll take this equation and perform complex conjugate. Why no complex conjugate here?
Because it's rare.
The potential, it's a real number. Okay, so what do I gain by that? I'll multiply it by the upper equation by psi complex conjugate and the lower one by psi. Okay, since I'm lazy, I'll just plug it in. Okay, here it doesn't matter the order because it's just a multiplication by a real number. Here it's important that it's before or after the differential operator. So what's written on the left-hand side?
Zero because we're squaring the phi, and then we are dividing the derivative. The negative one.
No, I don't know that the derivative of t of this guy is equal to this guy.
Oh, because we don't see the derivatives.
I don't know. I'm performing here a complex conjugate. It's not the same. The derivative is not the same function. But if I will subtract one from the other, that's the left-hand side. This minus this. This minus this is 0. Again, because potential is a real Why? Because the cross, if I'm performing the divergence here and here, it's equal and I get 0, and the other terms return to here.
Yeah, but I didn't understand what's the point by doing that.
Wait a minute. That's actually two interesting points. First, let me write down something that we had previously. Let me divide by IH bar. What is this guy?
Rho.
Rho. What is this guy?
G8.
J. Okay, so what did we learn from this whole exercise? Two things. One, that the Schrödinger equation corresponds to the continuity equations. It preserves continuity of psi squared. And second, we have seen a kind of intuition. How do I pull out a physical quantity out of the wave function? I got here current density. It's a complicated mathematical operation, but once give me psi, I have an algorithm to pull out the current density at a point. Okay, let's see if someone has good physical intuition. What does it tell you about wave functions? It tells you something interesting about wave functions. If I have a real wave function, what does it mean?
That we know what is going out and what is in.
There's no current density, because if psi is real, this guy minus this guy is always 0. So I can state that any wave function that describes development in time has to be, at least have a complex component in it. Otherwise, nothing changes. I don't know. Did you see a wave function of the hydrogen atom? At least one example. Those are real wave functions, meaning they don't develop in time. What does it mean? That this picture of an electron orbiting the atom is completely wrong. There's no change in time. So this symbol that you have seen in elementary, or the beginning of high school, of an electron orbiting, is nonsense. Well, you could understand it from the first part. Orbiting tells me that I know something about the trajectory. I don't know anything about the trajectory, therefore that picture must be wrong. So electronic orbits is a bad description of how an electron around an atom behaves, because it doesn't orbit. It means that it changes its position with time.
So what is changing?
Nothing. And we will describe it in details towards the end of this course. But if you ask what is the probability of finding an electron around a hydrogen atom at a given time, time is not important. You always have the same probability of measuring it at some point. It has, nevertheless, angular momentum. How can it have angular momentum without orbiting? Welcome to quantum mechanics. It has a definite value of angular momentum. It has even a definite component in the z direction. does the notation of NLN for the hydrogen atom mean anything to you? So N tells me the energy, L tells me what is the angular momentum, and N tells me what is the angular momentum in some direction, Z. So it has all these quantities, but it's not moving. What do I mean by not moving? I can't say if it's moving or not, because it's a meaningless state. I have a wave function that doesn't develop every time. Okay. So we spent a lot of time about the wave function, which we said that it contains all the physical properties of a particle. We gave even somewhat of an intuition. Now I'll give you a dictionary without proving it, because there's no proof. It's more intuition about how to use it, but you will start to understand something about it just by looking at the Schrödinger equation, which I will leave here for that purpose. Okay, so we have our wave function, as I said in the first part of this lecture. We still have to extract physical properties out of this wave function. In order to do that, we have a mathematical entity called an operator. Every physical quantity that is measurable is connected with an operator. Okay, what does it mean? Operators, we always use the notation of hat over it. This is the operator. It's in the language of function, of continuous function, it will be a differential operator. In the language of vectors, it will be a matrix. And we will see what are the mathematical conditions in order for something to be an operator that represents a physical quantity and what's not. Not any differential operator that you'll write down is a physical quantity. And we'll see what is the condition. The operator for position is the position. Meaning why is it so simple? Because we insisted on writing the wave function as psi of x. If if I decide to write it as psi of p, I'll have to transform also the operators, not only the wave function, and we'll learn how to do it. So we have energy. So momentum, which is a vector, like position, so it has three components, minus IH bar times dou to dou x, to dou y, to dou z. These are the three components. Potential is just the potential. So, a completely new way to look on Schrödinger equation. The Schrödinger equation is an energy operator that you are using with the wave function is equal to the classical mechanics. And Hamiltonian simply kinetic part of the Hamiltonian plus potential part of the Hamiltonian. So all you need in order to write down the Schrödinger equation for any system is to know the classical Hamiltonian and replace any physical quantity there with the corresponding operator. As I said, I wrote a dictionary. I didn't give you at the moment any explanation from where I pulled it out. So basically, all we do in this course is meet a problem, write down the Hamiltonian, write down the Schrödinger equation, solve it, tell you the development in time, answer questions. But just a moment. At the moment, I don't know to answer any questions. Right? I know the operators. I know to write the Schrödinger equation. Okay, I take some initial condition. And what do I do with it? Okay. First prescription on how I pull out physical expressions out of it, and I'm sorry that I'm doing it so ad hoc, but it's useful to me to understand, to see the definitions before we start to go into the deeper mathematical structure of this whole stuff. First thing is, if I have the operator, I know how to write the average of the physical quantity at any given time. What do I do? This is a general statement. The operator could be P, it could be X, it could be whatever. The average. In a moment, I'll go deeper. What is the average? Get your wave function, operate on it with the operator, multiply it by the complex conjugate, perform an integration, and you'll get the average. Okay, let's see that it makes sense for the only operators that we have some definition on how to perform this thing, which is position. What will you do with, how do you do an average of position? Okay, one way is work with a prescription, right? Okay, so average of X. Go back to my dictionary. I'm here talking about only X, not X, Y, Z. I can change the order. Which is exactly what I would have done if I would just take the definition of the probability density of finding the particle at point X times X, integrate, that's the average, right? What else? If I have a probability distribution, it takes a probability distribution, multiply by the value at this point, integrate over the whole distribution, get the average, right? Which, this definition after some simplification is exactly what I'm doing, right? So it makes sense at least. I want to calculate moments. Okay, x to some power. To calculate moments, I have to calculate x to some power. Exactly what I would have done in order to calculate the moment if someone would have given me a probability distribution. Nothing more, nothing less. Okay, so this actually is trivial. Why? Because we are working in a way for wave functions that are defined on x. Everything is simple in this case. If I want to calculate momentum, it's a bit more complicated. Therefore, usually, once we will know how to move from one representation to another, and we'll have questions regarding some quantity, we would like to work on a representation of a wave function that corresponds to that quantity. That makes life computationally much more simple. Although from the point of view of physics, it doesn't matter on what representation you work. It's the same as coordinate systems. The problem doesn't change because I define my coordinates in a different way. It could be much more complicated to solve if I chose a bad coordination that don't correspond well with the question. But the physics doesn't change. Okay, let's see something more interesting. What is the average energy?
Stay the same, yeah.
Well,
So the conservation of the energy, so the average energy should be the same.
right, but let's see if we get it out of the definition. Do I know to say something about it? Well, I have to stick my wave function into the Schrödinger equation. I'm not so sure I know how to solve it. But this is the definition. Okay, but the energy operator for any system that obeys the Schrödinger equation, meaning for all quantum mechanicals, is equal to the Hamiltonian. So let's write it down explicitly. So this guy is just the Hamiltonian. So
One is the potential, but we never know to solve. It will be two integrals
yeah, we can.
split integrals. So it will be with just one.
Well, that won't bring me anywhere because let's look what we have here. Here we have a number, right? Some energy. I don't know what psi. I have to know what is the energy. But if I'll ask what is the derivative of the energy, that is a conservation, right? Okay. I just wrote a derivative. So I have to show that this guy is equal 0, right? Well, integral over the whole this guy has to be 0. At least if V if it doesn't depend on T. If the potential depends on T, we can pump in energy into the system. Think about an electromagnetic wave. But if it's constant, it doesn't play anything. The first derivatives fall off. The second one, we have shown how to play with it, and it's indeed equal 0. We'll come back to it in the next lecture and do it step by step, but this is just an illustration. So basically, the average of any quantity principle we know how to calculate once we have our dictionary and wave function. Okay, now what are the questions? Why? Okay, that will be in the next few lectures because I have to build up the mathematical structure. But one thing that is important to remember at this stage, and no matter how many times I say it, I come to the exam and people continue to do this nonsense. An average of a physical quantity, what must it be? A real number. Now, one of the most ubiquitous mistakes that students do, forget about this complex conjugate, calculate, 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 get some numbers that has a complex component and walk away happy ever after. And this is one of the easiest checks that you did everything okay. If you didn't forget the complex here, if you didn't perform the integral correctly for some reason, if you didn't perform a derivative here correctly, most probably you will get a complex number. So I don't care so much if someone will write, well, I did a mistake in the math, I don't know why, but this result can't be true. I'm getting very angry on someone who leaves a complex number and says, well, the average position is 3i. That shows that he didn't understand it, perhaps I didn't teach correctly, but such a thing can't be. Physical quantity is a real number. Although the wave functions, the operators have complex quantities. Sometimes it's very easy to prove that some quantity is zero, because otherwise the calculation will give you a complex number, therefore it must be zero. For example, I can always tell you that the average, in order that the average of the momentum is not equal zero, the wave function has to have a complex component. Why? Let's write it down, and that will be the last thing we're doing today. And let's say px, just for brevity. Okay, let's assume psi if psi is real,
and the average of the
psi, the wave function is real. So I have here two real. The only place that I have
is the I
complex which comes before the integral. So the only way that I'll have here a non-complex number is if this integral is equal to 0. So I know that if psi is real, I know that Px is equal to 0 without performing any calculation. any problem of a particle in a box. You've seen probably some example in physics. The average momentum is 0. Of course, because it's in the box. If it had momentum, it would have left the box. And we'll see other consequences of this behavior further on in the course. Okay, so we'll stop here.
גל אמרנו זה דבר מרוכב, זה משהו ש...
אמפליטודת גל.
כן, האמפליטודה של הגל, זה משהו מרוכב.